Yeah, that's about the maximum face size you'll tolerate, I think. I need a shave. Hey everybody, what is this all about? I want to do a more in-depth video showing like lifting up the skirt. Is that one? Demonetized. Well, it's not monetized anyway. Of my sort of big scheme of world domination, how I look at the future of sim physics modding tools like physics creation tools. And I spoke about it before a little bit. What I would ideally have is one very big spreadsheet or whatever method, but I like spreadsheets, as some of you may know, where all the cars of a game are created. And instead of what I have now is one complicated spreadsheet that spits out one car. But then you have 10 cars in a sim. You can probably do that, but what if you have 20 or 50 cars in the sim? And also, you have to support these cars for a long time. Look at iRacing, it's over 10 years old. RF2, 8 years. Automobilista went for a long time. So having to support your content as you get more knowledge, as programmers and physics guys hopefully get smarter with time. Although I think, there's a peak somewhere. I'm 40 years old. Well, let's not go into that. But you improve your knowledge and you want to improve your physics, and it tends to happen, like tire models get updated. And then you have to go back to all the old content and update them one by one, or however you do it. So my theory is have one very big spreadsheet where you have the tire model sort of in there with a few input parameters, because a tire model you might need 100 parameters per tire as input parameters just to make the tire work, if not more. And that's not manageable if you're making 50 cars and you have to support it for 10 years. So my method is to, instead of thinking about all those 100 parameters for all those 100 cars, simplify it a little bit and see if there's a way to derive those 100 parameters from, say, 10 input parameters. Because while there are differences between certain different sizes of slick tire, there still will be some similarities. So you can probably come up with some rules and regulations that sort of simplify the input parameters and then still create very logical, realistic and consistent, that's the word, consistent output parameters. So in a sim, often you'll find some cars are great, some cars are not so great. And the more cars you have in a sim, the harder it is to keep all your content fresh and also very consistent with each other. With Automobilista, we received some praise for this, and somewhat rightly so, because Renato and me, we spent a lot of time with all the cars, and especially Renato kept tweaking it. But I always felt, well, it's a bit annoying. Some of these cars are a few years old now, and the suspension geometry, I learned some stuff. You want to improve, and you want the tools, the spreadsheet, to support the supporting of the sim, so the updating, continuous updating and improvement of the sim. Long story, not really short. What I'm convinced is possible is to make the entire car, so the suspension, tires, aero, everything in such a way so that you minimize the number of input parameters, still complicated, and the rules behind there are still very complicated, and the output is just as hardcore sim and probably more consistent and better than making one by one a car. In this video though, let me just remove my face, because it's about as much as I'll make people endure. I want to do something on the surface that's very simple. One of the things you have to do, if you make a sim with many cars, you have to figure out how heavy are the tires. That's a stupid question, you would ask, but it's still quite important. All the weights and inertias play a role. And the same goes for the rims. How heavy are they? So, is there a way without guessing? Because guesswork can also be bad. I mean, you can easily be 50% off with your best guess, or you can spend half an hour Googling. But perhaps we can summarize a sort of formula that approximates, comes close to the actual weights of these parts. So what are we doing? I'm programming a little bit, and I've made some models. So let's look at the tire weights first. So yes, I told you this was going to be fairly hardcore. Um, it loops through a whole bunch of known tires and it does its calculation. So what does that look like? Here we have a very long list of tires. So Michelin Cup tires, some all-season BF Goodrich, some Michelin all-seasons, but also some light truck tires, heavy truck tires, and some silly tires from like mega mining truck, that type of stuff, which is less important. And it goes all the way up to some racing tires that I know and a remote control scale tire, just to see how the model that I create that should predict the weight of the tire, if it matches or not. So a bunch of known data, which is very important when you do this stuff. So there are websites where you can find data for the tires. So I went online and looked at all the parameters of tires, Michelin tires, a bunch of that, all the properties of tires, the Cup tires. So we have a varying size of tire with the known weight and sort of the properties. Hoosier has a nice database as well with some slick-ish tires for rally for like what is it called? Parking lot stuff they often use in in the US. So we have a big range of data. That's super important because you make a model, you want to compare it to real data, and you have to find it, and it has to be sort of trustworthy. So a bunch of data. So we know how heavy the tires are, and they have some properties. In this case, they have a diameter in inches. Where are we? Here we are. So they have a certain width, millimeters, aspect ratio. They have a rim diameter in inches. Typically that's inches, don't know why. Then there are a subjective parameter, the slickness. So if it's 1, it's a full slick, and if it's 0, it will be a super knobbly off-road tire. And I use that to compute the thickness of the thread blocks, which will add to the weight and the inertia, because we have some data for the Bridgestone tires from the GP2 car from a very long time ago. We have some data for the wet and the dry tires, so we can see how much weight is added from the extra thread that's needed to get the grooves, and there's more thickness there. So a whole bunch of input data then, that's great. And then we model a model that loops through all the big list that we saw there, which is set up here. It reads all the data, so for each car we have the width, the aspect ratio, the rim size, there's a slickness, and also sort of a rated pressure, because it's sort of an average pressure that you probably run the tire at most of the time. So about 2 bar for a GT tire, 1.5 bar for a slick, 2.5-ish bar for a road tire, and perhaps 6 bar for a big truck tire. I use those as input parameters, and then I make some calculations here, which what the radius is, and the area of the sidewall, area of the thread, the volume inside the tire, that sort of stuff. And then I'm sort of constructing a very simple model of the tire with 2 sidewalls and like a thread area over it, like a ring over it with the rubber that meets the road. But we want to have some modifiers. So the way I did it, and there's many ways to do it, and this is not necessarily the most elegant or even accurate or best way to do it, but the way I did it is that I go with a certain starting point. So here we have those. The starting point pressure is taken from the spreadsheet, so perhaps 2.5 bar is sort of an average pressure. And then if the pressure of the tire that I'm modeling is different from this base pressure, I can sort of multiply a value with it. So I get like a factor that comes out of that. So if my base pressure is 2.5 bar, but my actual tire that I'm currently looking at, like a truck tire, is 5 bar, and that difference might be a factor of 2. And I can use that because perhaps a more high pressure tire will have to have a stronger, heavier construction in order to not explode. So here this gives me a curve effectively that changes a multiplier as the pressure of the tire deviates from my base pressure. I do the same for radius, so if the radius is bigger, perhaps that has some effect of a multiplier I'll use later for the thickness of the material, for example, the width as well, and also the rim. So these are a bunch of multipliers with a power. So the difference, as the difference grows between the tire I'm looking at and the reference value, you can sort of exponentially change the factor that comes out, the modifier. So here we have a few modifiers, and then we combine them into one modifier. So perhaps a car tire will have a total modifier of 0.5, like half, and a truck tire will end up with a total modifier of 2, for example. Then we go ahead and we have a few parts of the tire, the carcass, which is the sidewalls, and I also use this like the thread area, but not the actual rubber, just the construction and the plies and stuff beneath the rubber that meets the road surface. So there's a density, in just like the material has a density, like it's the weight per cubic meter, for example. So we have a density value, and then I will calculate the thickness and area, and I get the volume of my carcass. And when you have your volume, you can calculate the mass. And there's a minimum thickness, perhaps 1 millimeter, because there's always going to be some material. And we're going to calculate the sort of the thickness by multiplying with that adjustment modifier that we did here. So we have a starting point thickness of the thread and the carcass, perhaps 5 millimeters. Then we look at the total factor here. For a car tire, it might be 0.5. And then the carcass thickness, instead of 5 millimeters, becomes 2.5 millimeters. And when you know how thick it is, and you know the area, you can do the volume and you can calculate the weight, the mass of the carcass. Same for the thread. So that's a little confusing, and it depends how you want to name it. But this is my code, and I can make it as confusing as I wish. So the thread, it consists of a rubber layer. And if you have a slick tire, that's it. But if you have a road tire or a rain tire, there will be some thread blocks as well. So here I calculate sort of again the basic thickness, perhaps 3 millimeters for a slick tire of a certain size. That's your rubber thickness. And then if it's not a slick, because we have that slickness parameter, if it's not a slick, it will add a little bit of thickness there because we have thread blocks. And then when you have the thickness and you have the area and you have the density, you can calculate the mass of that as well. And finally, you can add them all up. So what we've constructed is basically a simple model with two sidewalls, a thread, like plies and stuff, and then the rubber on top. And it's sort of physical, and it's based on modifying some initial parameters based on the size of the tire, effectively, and the slickness. And how close does that get? And inertia is very important, but we won't look at inertia now. So back to the spreadsheet here. Here we have a whole bunch of tires, and we start here. These are the first two, the RC car and the big ass mining truck car, so that's not too important. And then we get some car tires, some Bridgestone stuff, some single seaters. So these few are racing tires. Then we get the Hoosier slicks. Then we get the Michelin tires. And what you see here is the weight of the tire. In blue, that's the actual weight. So here this tire is about 10 kilos. You know, this is the weight of the tire. And in orange, that's the model that we just saw that replicates like a physical shape with density and thickness and weight of the tire. How close that gets. So here we have racing tires, semi-slick-ish tires. Here we have a bunch of road tires. Here we have light truck tires. Here we have heavy truck tires. And you can see that our model, the orange line, predicts the actual weight that we got from the big database and from our real racing data very closely indeed. So the model might be a little not transparent, but it's super accurate, at least, you know, give or take a few percent. So with the racing tires, for example, the error, here's a 0, is like within 10%-ish. So we know just by entering the size of the tire, and if it's a slick or halfway through between a slick and a very knobbly tire, we just enter the size, and it doesn't matter if it's a kart tire or a GT tire or a slick tire, it will be very close. And even if we do a truck tire, which we see here, it's still incredibly close with the weights. Light truck tires are a little overweight for some reason, but here you can see that one model, that's 1 day of work, and after that I will never have to think about the weight of the tire again. It also allows me to calculate the inertia of the tire, the rotating, the resistance to rotation and acceleration and braking of the tire. Because that's now easy to do because we have a physical model. We have sidewalls with a certain dimension, and we know where that is. We have the thread, we know where that is, how heavy it is, and then you can calculate the inertia as well. So that's really important. And in order to tweak this, I've put all the parameters here on a sheet. So I can change all these numbers, which make some sense to me and probably don't to you, but that's fine. So let's see what happens if we make some changes. So the carcass density is the material, which is some rubber, some nylon, perhaps some steel. So let's make that heavier, and you'll see that everything will change. You see, and now my predicted results are, because I've made the tire heavier, I didn't change the thickness, but I changed the density of the material, and now I'm overweight with my prediction. And now we're good again. You can also see the thread blocks that change, like if it's not a complete slick, but it adds some thread depth if it's not a slick, is now a certain percentage of the radius of the tire. If I change that, we get a few dips. So now rain tires don't get heavier, and here we have some rain tires, the Bridgestone GP2 tires. They are now suddenly underweight because we no longer add thickness of the rubber for rain tires. If we do, it comes right back and it's fine again. So having these numbers, I mean, the model is one thing. It has, to be honest, too many parameters. I went overboard with it, but it does work fine now, and I'm sort of curious if I can make a way simpler model that is 98% as good. But anyway, I can change the parameters here quite easily and see what happens. So, for example, if I want to make the weight more sensitive to the radius of the tire, I can change its multiplier. And now you see the bigger tires, the truck tires, get heavier because it's more sensitive to growing radius, which the big tires have. And the nice thing about having the base radius of 0.3, that's sort of a normal-ish tire, we never mess with that. The results will always be the same there, but once the radius of the tire is different from this base radius, then we'll get a different result. So if we overdo it, then yeah, our truck tires are really heavy. If we don't do it enough, you'll see that my normal tires are still fairly normal, but the bigger they get, the more underweight they will become. So this model and tweaking it this way is fairly handy. I also make a carcass thickness, thread thickness, carcass mass, and thread mass. That's also plotted here. So it works very well for all manner of road tires, racing tires, and also for truck tires. And just for giggles, it's not quite there for a remote control tire. If like a 1 to 10 scale car, it's overweight because I think it should be about 25 grams and it is 45 grams, so that's 80% overweight. But funny enough, this incredibly monster mega mining truck tire, I get 5,000 kilos, which is identical to the real tire. So even for super big tires and super tiny tires, the weight error is quite small. The percentage is quite large, but it's only a few grams. So this model works very well for tiny tires to huge tires, and you never have to think about that again. So think about it, how much time, if you have to make 200 cars for a game, like it's Gran Turismo or something, how much time you would save, because this is 1 day of work, and then you just enter the size of the tire and its slickness, and it will come up with the weights and inertias for you. So only a tiny part of a spreadsheet that I want to have where everything is made like this, but you can see the benefit of having a model. Secondly, we also have the RIMS, which there is a database as well. Somewhere online you can find this database with a whole bunch of rims with the diameter, the width, the weight, and that sort of stuff. So you can see trends in there. So I've done pretty much the same. I've averaged, like the database has a whole bunch of tires, wheels from a whole bunch of different manufacturers, and I've averaged them for a certain diameter and width, and then what's sort of the average weight of that. And I've made a model, again, pretty much the same way, still not possibly the best way, but the way that works for me. So we loop through the data again, so we have a big list, database averages, we have some race and truck tire rim data here, and then we have a bunch of BBS and other rims there. So it looks at these parameters, and then it does the model calculations and spits out the weights of the rim. And this one was a little trickier, and it's still not, well, it's more than fine. So what I did here is also we have the density of the material, which is, in case of aluminium, it's 2700 kilograms per cubic meter. So here I make a model that's effectively a ring, like just like the thread on a tire. It's just like a ring with a certain width. And we also have those multipliers again with powers and multipliers, so we can change when the tire or the rim is different from this base value, we can start to modify the outcome. And we have that for the rim diameter. There's a lip sort of that stops the tire from falling off, so there's like a vertical lip on each end and the size of that. So I really construct a physical model, a simple one, but a physical model for the rim. So there's like a U-shaped thing that has the two lips on the side, and then the flat, like a ring of the rim. And we have the spokes and the hubs, which have a certain width again, and also modifiers just in case. And then I make spokes with a certain length. And then if it's different, we get a modifier for the length. We have a central hole. And we also have the spokes that don't quite run until the edge of the rim. They typically end a little sooner than that. And some more parameters. And you can see what we've done here. If we compare it to the database, which goes from 13 inch to 19 inch, from 5 inch width to like 11 inches. So this is a really large range of sizes. Road car wheels, that is, but you know, still a big spread. And here we have again the results of the model in orange, where the weight goes up. If we go from like 13 inches, 5 inches width to 19 inches and 10 inches wide, there the weight goes up from like 4 to like 12 kilos. And our model stays with the real blue data very accurately. And if we plot the differences here, you see that effectively it's within 10% again of the average of the big database. So we're very close there, that's nice. I also have a density multiplier in here because not all wheels are made from aluminium. Some are magnesium, which is lighter, and of course there are differences per brand and model rim. You can't escape that. So for carbon rims you might use a density factor of 0.4. For like high quality magnesium racing wheels you could value of 0.75. If we do that and we compare the data for some known rims for racing cars, so there's GT3 from homologation for the Lamborghini, Formula 3 GP2, which I believe are carbon, and I'm not even sure actually. No, they're probably not carbon, they're probably magnesium. Anyway, and kart rims, you can see that using the correct density, or just a value for the density, because not all materials are equal, you can get really close to the real data for racing rims as well. And here we have some BBS rims that are that's a bit less spread, like 17 to 19 inch diameter with different sizes, but it goes up more or less correctly. Same for the Enkai rims over their range. So these here are 15 to 19 inch. You can see the model is very close. So just like the tires, we have now constructed a simple model of the rim. That's physical, it has dimensions and material density. Gets really close to a whole bunch of data that we found, be it racing tires or whatever. So I just have to know the size of the tire, the rim, and a subjective density value. So 1 if it's just a good road tire rim, 0.75 if it's a race tire, perhaps 0.4 if it's a super lightweight racing tire, and then I don't know if carbon rims will be more popular, but you can add your multiplier there. So there's a minimal number of parameters you have to enter, 4 in this case, and you'll get within a few percent of actual rim weights and inertias. So it's all really sort of ugly and work in progress here, but you can sort of see the benefit of doing all these things, which sounds like a lot of work just to come up with some weights and inertias, but you only have to do it once, and then you can apply it to your physics spreadsheet, and all the cars will get correct, or at least logically derived, non-guessed properties for these tires. So, this is probably my way of making sure my channel never grows, but I'm sure there's one or two of you out there who found this interesting. And in the meantime, I've been sort of doing this really occasionally because there's not a lot of time. I've done the same for load sensitivity for tires and also aero maps. I can now make aero maps that make sense and that have a certain sensitivity, adjustable sensitivity for pitch and ride height, and with just a few parameters, and I get aero maps that match like the LARA data. So there are many ways, not just for these simple things like wheel weights, but for aero as well, and I'm sure I can do it for engines. I've already done it actually. I've done quite a few things. Where did the time come from? I don't know. But doing it like this, minimizing the number of parameters you have to enter, but making sure there's a solid model behind it, so you don't need a million parameters and there's no guesswork, and it's a solid model that's guaranteed to give you good results. So that's my philosophy, and this is just a tiny wee little, just a tip and only for a minute sort of thing. Yeah, that's it for now, and catch you guys later.